Hello, this is Concrete Path. Here we have the lecture that's related to calculations of that unit weight, calculations of unit weight of the soil. That's determination of unit weight. Let's go for that. Unit weight measurement we got right. So unit weight that we write as, if you talk about bulk unit weight, that's your gamma bulk. It's actually weight of soil by volume of soil. Weight of soil by volume of soil. So we have different methods. For this, we have different methods. So the methods here, those methods differ. The methods differ in calculations of volume. In volume calculation, because your weight calculation is accurate, but your volume calculation is difficult. That means it's not accurate. So for that, for calculating the volume, we have different approaches to get the volume of soil. So based on this one, we have first method that we call as core cutter method. Core cutter method. Core cutter method. Core cutter method. So we have a core cutter that we have in this fashion. Some sort of cylinder is there. Core cutter, we call that as core cutter. It's having some diameter of d. It's having some height of h, such that your volume is there of that particular core. This is a metal cylinder, we can say, hollow cylinder, metal. So of that core, we can write here volume of that core is actually, let's say, pi by 4 d square h, and this is almost equals to 1000 centimeter cube. 1000 centimeter cube. Okay. Now we are going to have, let's say the weight here is W1, weight of the core. This is the weight of the core only. Now we are going to the field. Let's go to the field. So this is your field method. We are going to take this with ourselves, with us. So finally we are going to drive it. We are going to drive it. We are going to drive it because of hammer, by the hammer action. So we are having hammer with us also. So by the hammer, we're going to drive it inside the ground. So if this was your ground level, now your core cutter has reached to the ground, inside the ground. Now your core cutter is somewhere here. This is our core cutter. And in that top, we have one tool that we call as dolly. This is your dolly, on which we strike from the hammer. From the hammer, we strike on the dolly. Then finally it stucks to the ground. So then from that, now we can say your soil has been collected inside that, what you call as core. So finally I would say you remove that, you excavate that again. Now this is your core with the what you call as soil from the ground. So this is your W2, that is soil plus cutter, that's core cutter. Soil plus core cutter. Soil plus core cutter, that is the weight to W2. Soil plus core cutter. Now we are going to take a representative fraction, a representative sample. So we are going to take, when we kind of remove the soil from the core cutter now in the lab. Now we're going to take this one to the lab. Then from finally let's remove the what you call as soil from this one. Let's remove the soil. Now we are going to take a bit of soil from the here, a bit of soil from the mid, a bit of soil from the other side also, such that these three, a net value of, let's say, some 40 grams, 30 grams, let's say 40 grams we have to take, that we call as the representative sample for water content determination. We're going to measure the water content from this one, that we know how to calculate water content based on own drying method. That is a field, that is a lab test, standard lab test, own drying. From that, get the value of water content. So once we got the water content, and we know how much soil is there in the soil, this, I would say, what is the volume of soil we have excavated? What is the volume of soil? Can you tell me? I would say your volume of soil is actually W2 minus W1. W2 minus W1. So your weight of soil is actually W2 minus W1. Once I got the weight of soil, I would say, what is the density? What is the bulk unit density? Bulk unit weight. That is actually W2 minus W1 divided by total volume of V, that we already know. That's V. That's 1000 centimeter cube, or if the dimensions are given you in terms of that pi by 4 d square h, so we can calculate volume. So you got the bulk unit weight, and from that you can get the dry unit weight based on the equation that we have this equation. And from water content, you calculated water content, and finally you can write dry unit weight. You can solve a dry unit weight of that soil. So this is the method we have. Okay. So initially that there is a core cutter of weight W1. We are going to uh, drive it into the ground such that it collects some soil also. That the soil here, total soil is equals to W2 minus W1, and from that take a representative sample of such that there is some water content W, and from that we can calculate dry unit weight. Okay, and that means this method should be suitable for some sort of soil. So how can this what call as core going to collect some soil when you're driving that particular core inside into the ground? It should collect a soil. It should collect a soil. Soil should be collected. Soil must be collected. We can write must be collected. That means what that means? That means the soil should get lifted up, or we can say your soil should be cohesive soil. Soil should be cohesive. Your your core cutter should go inside into the ground. That means the soil should not be stony type. It should not be stony. It should not be gravelly type. It should not be stony type. It should not be gravelly type. It should not be sandy type, because sand is not going to be lifted up into the core, because there is no cohesion that is going to fall down. So in these kind of soils we are not going to use this method. So this method is used for cohesive soils and the soils which are very soft soils. Cohesive soft soils, we prefer this method in which the that core cutter can be easily driven into the ground. So that's your core cutter method use. Okay, let's go to the second one. So this cohesive, we also call them as fine grained soils. That's clay slates, fine grained soils, fine grained soils. Let's go to the second method. Let's go to the second method that we call as water displacement method. Water displacement method. Water displacement method. Very important one. Water displacement method. So all these methods are differ in the calculations of volume of soil. So we need to only calculate volume of soil. What is the volume of soil? For that calculations, all these methods differ. So this second method is also saying that how to calculate volume of soil. So that's weight of soil is easy to calculate. I would say you take any sample, there is some weight of soil. Okay, there's some volume of soil. We need to calculate what is the volume of soil. From that, we can say what is the bulk unit weight. That's very easy then. If once you got the volume of soil, it's then easy to calculate what is the bulk unit weight, because weight of solid is easy to calculate. You take the sample, place on the weighing machine, that give you the weight of solids. That's easy. But volume of soil is important one to calculate. So second method here is water displacement method. It's talking about that you place the soil inside the water. That means once the soil is in contact with the water, once the soil is in contact with the water, it would disintegrate. It would lose the shape. It would disintegrate. That means the volume would be lost. Volume, that kind of thing. You would be getting different volume now. That soil disintegrates. To overcome this effect, we are saying let's make a soil sample in some sort of regular shape. Let's make a soil sample in some sort of a ball. Let's say this is our soil sample. In this way, this is our soil sample of weight W1. Let's say this is only soil sample W1. We are going to make some sort of ball, regular shape. So then we have molten wax. We have molten wax. Molten wax is there. Let's say there is some molten wax here, and we are going to dip this one. We are going to dip this one. We are going to dip this one here inside that. Let's say that this is molten wax. This is molten wax. Okay. And that we are going to dip this one. Let's say we have dipped that inside, and based on that, there's now finally your configuration of that specimen would now be in this way. Such that it's having some layer from the top, it's having some layer all over the surface of that what you call as molten wax. That's the covering, external covering for that soil sample. So that's your what you call as wax. Okay. Now this one is having some weight of W2. So why we are using this wax? So that's used to make that it makes the soil impervious to water. Impervious. That means water cannot enter now into the soil sample. So to make the soil impervious, we are using that wax. So because the method here is water displacement method, we are going to use the water. So we have one bath tub kind of thing that we call as water displacement container. This is water displacement container. Now we are going to place this one. We are going to place this one. Let's place this one here. We are going to place that what you call as. Let's go for that. So initially there was water. Let's say that initially there was water up to this level. This was initial level of water, and there is one tube. Let's say there's one tube what you call as outflow tube. Let's say there's some outflow tube kind of assembly, and there's one more container there that is trying to collect how much water has been lost. Now once we place this what you call as this assembly inside that what you call as container, your water is going to lost. Your water is going to lost because of that what you call as buoyant force, because of that Archimedes. So some water has been lost. So here the volume of water lost. So we can write here your volume of water lost from the container is actually equals to volume of mix, volume of sample. We can write volume of soil sample, and this sample we are saying this is our sample. That is it's having some volume of soil plus volume of wax. That's your sample. Okay. Now we got that. Now this is easy to calculate. This part is easy to calculate. We know that how much water has been lost, how much volume of water that is lost. That's easy. Once we got that value, that's easy to calculate. But it's not actually what is the volume of soil. This is not the actual volume of soil. But your actual volume of soil is actually some volume of soil plus that difference of the two. So your final calculation is that what is the volume of soil? That is our main part. That is actually total volume of sample we got from this relation we have with the volume of lost water. So once we got the volume of sample, then we subtract volume of wax. Now we need to say what is the volume of wax in order to get the volume of soil. So volume of wax can be calculated in this way, that once our test is over, once our test has been over, then we say that let's try to remove that all. Let's try to remove that all what you call as peeling. Let's try to peel that off. Let's try to peel that wax off. So this we are going to remove now. Carefully remove. Now we are going to carefully remove this wax. It would be having some weight of WP. We call it as paraffin wax. Paraffin wax is there. So we can say there it would be having some weight of WP. You calculate that. Okay. You calculate that WP. Once you calculated that WP, you would be knowing that what is the density of that, what is the unit weight of paraffin, we also know. And from there we can calculate what is the volume of paraffin. We have used it for our sample. So we can write here that volume of wax is actually equals to that weight of paraffin that we calculated divided by that gamma of paraffin. So your volume of soil is actually volume of sample minus weight of paraffin divided by gamma of paraffin, where your volume of sample is calculated from the that what was the total volume of water lost from the outflow. Okay. So once we got the volume of soil, we already know how much weight of soil was there initially, W1. We know that what is the weight of soil. So that finally we can write. Yeah. One more thing is there. Can you tell me what is the weight of paraffin from the two these readings we have? Can you tell me what is the weight of paraffin? So actually the weight of paraffin is actually W2 minus W1. Can you see that? Weight of paraffin is actually W2 minus W1. So finally I would say your weight of paraffin is actually W2 minus W1. So final equation I can have that volume of soil is actually volume of sample minus W2 minus W1 divided by gamma of paraffin. So you got this volume of soil. Now I would say, what is the density? What is the bulk unit weight of the soil? That would be actually equals to weight of soil divided by volume of V. This is our final equation. And from finally you can have a representative sample also. If you take from the center, if you take from the center some weight of soil, let's say some 10 grams, 25, 10, 12 grams. You take a small part of that from the center for calculations of water content, W, small w. So you got the water content also. Then finally you can get dry unit weight is equals to bulk unit weight plus that 1 by 1 that divided by 1 plus W. Okay, let's revise it one more time. So we have this water displacement method. Because water what you call as water, when we place it in because when we place the soil in the water, it's going to disintegrate, but we need to calculate volume of soil such that it's not going to disintegrate. So for that we are going to use what you call as paraffin wax to make the soil impervious. So we would say we have a soil of volume V1, or we can say volume of soil Vs, volume of soil V, capital V. Okay, and it's having some weight of W1 soil sample. After that we are going to dip into the molten wax such that it's now having some weight of W2 because of paraffin also. So where your weight of paraffin is actually difference of W2 minus W1. So that's your WP. And because of this, now we are going to place this whole assembly, that is the sample, we call it a sample now, into that what you call as water displacement container. And there's an outflow tube that's collecting how much water has been lost, because when we dip that sample here, so that we say that your volume of sample is actually is actually how much volume has been lost from the outflow tube. So that we can calculate. So volume of sample we can calculate. We got the volume of sample. Now we also know what is the volume of X. What is the volume of X? That we calculate that is the actually weight of paraffin divided by unit weight of paraffin. And weight of paraffin we calculated as W2 minus W1, and we already know what is the unit weight of paraffin, and usually its value it's in the range somewhat value around some value of 9.7904 kilonewton per meter cube. Some value around this range, that would be provided to you in the calculations. And once we got that, you can say what is the total volume of soil, and we also already know what is the volume, what was the weight of soil sample, that was W1. So you can solve bulk unit weight W1 by total volume of soil, that's W1 by V. Okay, so let's go for the one problem related to this method. Let's go to the one problem related to that concept. We can have a first problem related to that method, water displacement. Let's say that we have a clay sample. There is a clay sample. It's coated with what you call as coated with paraffin wax. So that the assembly now becomes in this way. Okay, so it's having some weight of W2 equals to 697.5 grams. And initially the sample was only W1, and the weight here was 690 grams. And we have water content in the soil sample. We have determined the water content also for the sample, that is water content of 18%. Water content is 18%, and all the sample is immersed in water. When it's saying that all the sample is immersed in water, that means it's talking about that volume of all the sample is actually some volume lost from the tube, so that you can calculate total volume of the sample. All sample is immersed in water. It's immersed in water, and we say water displaced from that container. Water displaced is equals to 355 milliliters. So this is the water lost, and your specific gravity for the solids, specific gravity for the soil solids is 2.7, and specific gravity for the paraffin wax is actually 0.89. Now we need to calculate unit weight, bulk unit weight, dry unit weight, void ratio, and degree of saturation for that soil sample. So these data we need to calculate. bulk dry ES, bulk dry ES. So what's the data we have? I would say based on the equation, based on this equation, we can calculate what is the volume of soil. We can write what is the volume of soil. Can we write what is the volume of soil? I would write volume of soil. Volume of soil is actually V equals to volume of sample minus W2 minus W1 divided by gamma of paraffin. Now let's substitute those values. What is the total volume that is displaced? So I would say this part is actually equals to volume of sample. So I would write 355 milliliters. And one thing you can write that 1 milliliter is actually 1 centimeter cube. By this result, that 1 milliliter is 10 to the power minus 3 liters, and your liter is actually 10 to the power minus 3 meter cube. And then finally you can write that is actually 10 to the power minus 6 meter cube. So your your 1 meter is 100 centimeters. So finally you can write this is also equals to 1 centimeter cube. So your 1 milliliter is equals to 1 centimeter cube, 1 cc. Okay, now we need to say you got this volume of sample as 355 milliliters. Now what is the difference of W2 minus W1? W2 minus W1 is given you in terms of grams. So our density would be in terms of grams. So your calculations would be in terms of those milliliters and grams. So let's substitute that value. I would say your W2 minus W1 can be solved as difference of the two. That is 697.5. Let's write here 697.5 minus 690. This is actually mass of paraffin. So that is 7.5 grams. Mass of paraffin, that is 7.5 grams. We can write here grams G. So that is the difference. That is 7.5 grams. 7.5 grams. Okay. And divided by gamma P. What is the unit weight of paraffin? Now, if we are calculating in terms of that small rho, if you are calculating in terms of rho, that is the density. What is the density of water? That is 1000 kg per meter cube. 1000 kg per meter cube. But if you are saying in terms of grams, I would say gram per centimeter cube. So density of water in terms of grams is 1 gram per centimeter cube. Similarly, if you are saying what is the density for paraffin, that would be some specific gravity of that paraffin into rho W. Can we write that? Based on the relation that what is the specific gravity of paraffin, that is actually density of paraffin divided by density of water. So we can substitute that value here. That is Gp into rho W. Your Gp of what was the Gp that was given to you? Paraffin 0.89. 0.89 we can write 0.89 into unit weight of water in terms of density. That's 1 gram per centimeter cube, 1 gram per cc. So this is the value that's actually from this calculation, Gp times rho W. Okay. So from this calculation we can say the volume of soil is coming to be equals to 346.573 milliliters. That's also we can say 346.573 centimeter cube. Okay. Once we got the volume of soil, can you tell me now what is the bulk unit weight? Bulk density. So we can solve that bulk density of the soil is actually equals to mass of the soil divided by density divided by volume of soil. Your mass of the soil is actually how much? 690 W1. 690 is there. 690 we can write W1. Where your W1 is actually 690 grams divided by volume of soil. What is the volume of soil we got? 346,573. 346,573. It's centimeter cube. So your density becomes some value of 1.99 gram per centimeter cube. If you want to now calculate in terms of that unit weight, bulk unit weight, I would say this is 1.99 times 9.81 kilonewton per meter cube. That's coming to be equals to 19.53 kilonewton per meter cube. Now we can directly calculate what is the dry unit weight. We need to calculate dry unit weight, that is bulk unit weight divided by 1 plus water content. What is the water content that was given to you? 18%. Water content 18%, so we write 0.18. So that's coming to be equals to 16.5517 kilonewton per meter cube. Now we need to calculate that void ratio and degree of saturation. Void ratio and degree of saturation. We have the equation that Sebag SE equals to WG. Once I got the value of, I need to calculate somehow value of E. Then after that I can calculate S. So based on the equation of gamma dry, we can calculate that this is also equals to G gamma W1 plus E. G gamma W1 plus E. Substitute the value of G that was given to you, and gamma W we know that 1 plus E we already know that is all equals to gamma dry, and substitute the value of gamma dry, so your value of E would be equals to, your value of E comes to be equals to 0.60. So once you got the value of E, now we can solve for the value of S. We can solve now value of S, that is WG by E. WG by E, the value of W was given to you, water content of 18%, and water content of 18%, specific gravity of solid is 2.7 divided by void ratio of 0.60. Your degree of saturation is 81%, that is 0.81. That was the end of this problem. That was the end of this problem. That's water displacement method. Let's take the third method. The third method for your calculations of gamma bulk unit weight of the soil, that we call as sand replacement method. Sand replacement method. Sand replacement method. This is the third method we have. So this method is actually useful that there's some ground. Okay. Now we are going to excavate a small area. Let's excavate small volume. So this part we have to excavate. Let's say we have excavated this area here. Let's say we have excavated this area. Let's try to show that. Let's say we have excavated this part of the area. Now it might not be regular, so let's say that there is some irregularity. We don't know exactly how much volume we have excavated. Let's say we have excavated this much area. So this part is excavated. Okay, we have excavated small area. From that, let's calculate the weight of soil. That is easy. We'll excavate some soil that we can say how much weight we have excavated. That is easy to calculate. Now we would say how much volume we have excavated. What is the volume of soil we have excavated? Can you tell me what is the volume we have excavated? We don't know how much volume we have excavated. For that, we use the concept of sand replacement method. We have this concept of sand replacement method. What we are doing here is that, so we are doing one thing. So to calculate the volume of soil excavated, for that we are going to this method. Let's say that this is the volume of soil excavated. This is your ground level, and we place one, what you call as calibrated cylinder. There is one thing that's called as calibrated cylinder, and one more is there that is called as cone. So we have these two. Let's say that we have here that attached. We have attached that here. Let's say this is your handle. This is handle, okay. And we have some shutter also. So place it somewhere here. Let's say there's some shuttle. Where is that? Let's say there's some shutter somewhere here. This is your shutter. And we have some sort of assembly that we call as cone assembly. We have a cone assembly here. Cone assembly is there. Cone assembly. So that acts as a cone, such that you can have from the top there is some sand. Place it in that cylinder. Place it inside that cylinder. There is some what you call as sand. There is some sand also inside that calibrated cylinder, and we are going to pour that sand now into that excavated area. Now we are going to pour that inside that excavated area. So we would say it is going to get filled now, because it's going to fill it now, because it's going to now get filled, so some part of the volume from the top is going to be lost. So finally your volume from the top would be somewhere here. So this is the volume of sand lost from the calibrated cylinder, such that it has been occupied by the volume of what you call as sand in the cone and volume of sand in the hole. So that volume of what you call as volume lost from the calibrated cylinder is actually volume lost from the calibrated cylinder is actually how much? That's actually volume of hole plus volume of cone. So we are filling that cone and hole, but your cone is not in the calculations for our calculations. Our volume of hole is actually volume of soil that we have excavated. So that sand is filling that hole, and that sand is filling that hole and cone. So if I know that what is the if I know somehow that what is the unit weight of sand, if I know what is the unit weight of sand and what is the volume it's filling in the hole, and I can say based on this relation I would say what is the volume of hole. Yeah, I'm saying this one that uh, this let's see what I am saying. Okay, I say that you are filling some, you don't know actually how much is the volume of hole. We are going to perform it in this way, that we are going to perform it in this way. We don't perform in terms of volume, we perform it in terms of mass. So initially there was some reading of, let's say the calibrated cylinder was in this way. This was your cylinder, it was having some that is what you call as weight. Let's say this, it was having some weight of W1. It was having some weight of W1. This was the that cylinder, calibrated cylinder. Now because it is now filling, some sand is going to be lost for the hole and the cone. So I would say some weight lost now. Weight lost is actually weight of sand in the cone and weight of the sand in the hole. So this is the weight of lost sand is actually sand, weight of sand in the cone and weight of sand in the hole. I would say what is the weight of sand in the hole? What is the weight of sand in the hole? So that we can calculate. If I know that what is the weight in the cone, that we also can calculate. That you can see that tutorial how to perform that test. So we see that how much volume of the how much weight of the sand is placed in the cone, that we also can calculate. Once we got that, once we also got how much lost of the that total weight of the sand is there because of the cone and hole, then finally you can say what is the total weight of the sand inside the hole. So once we got that WSH, we also know what is the unit weight of the sand. We also know what is the unit weight of the sand, and from this hole, from the excavated area, this was your excavated area. In that you are putting that WSH. We have this WSH of unit weight gamma S. So from that you can get what is the volume of that pit. What is the volume of that excavated area? So once we got that volume of the excavated area, then we would say that sand replacement method is there. So we can say what is the gamma bulk? That's actually weight of soil by volume of that excavated area. So that is the procedure we have. That is the procedure we have. So in this way we are going to perform. Let's try to repeat a little bit one more time, that we are going to want the calculations of volume of excavated area. Let's write it as volume of hole. So volume of hole is actually volume of soil. So for calculations of volume of soil, we have to calculate volume of hole. So this part we have to calculate what is the volume of hole. For that, we are using that calibrated cylinder. Let's say the weight inside that calibrated cylinder initially was W1, total weight of W1. Now, when we try to fill that cone, and what you call as hole, when you try to fill that cone and hole, so your W2 reading of the cylinder is somewhat here. That means only now the sand is only this much. W2 sand amount of W2 amount of sand is only in the cylinder now. That means there is some loss of weight in the cylinder, that is actually close to weight of the sand in the cone and weight of the sand in the hole. And we also know when we lift off that all the assembly, then we know how much weight is there inside the cone. Then when we lift that up, we know how much sand was there. We estimate the value. Let's estimate the value of weight of sand in the whole, what you call as cone. We also got this as WSC, right? Write it as. So we write what is the sand, what is the weight of sand in the hole? That is actually W lost minus WSC. So this is our one more reading. This is our one more reading, and from that, once we got that how much WSH is there, how much weight of sand is there in the hole of unit weight gamma sand, from that get the value of volume of hole. So that's our task. That is our task to perform. Let's take one problem that we can understand. Then we can understand that. Let's take that one problem that we have site at Roorkee. We have a site at Roorkee for the residential complex building for this one, what you call as a residential complex. We want to make a residential complex building, complex site. Okay, right. So we excavated that weight of soil excavated was equals to 761.25 grams. Okay, and it's also given that weight of sand plus slender, that we write as W1. It was initially 10500 grams. That was in this way, that we have the cylinder, and we have this calibrated cylinder. It's having some weight of W1, and there is some cylinder is there. It's having some weight of W cylinder, plus we have some sand also, such that W1 is finally 10500 grams. After that, we have second stage, that is weight of sand plus cylinder. After pouring in hole, after pouring some sand in hole, and some sand in cone. So that means it's talking about W2, that we write here, W2. What was that? So this is talking about that particular second reading. So that was your W2. That's some stuff is lost. Some stuff is lost because of cone and hole. So I would say the loss that we can solve for in the solution. Let's forget that. I would say the weight of sand and the cylinder after pouring hole and cone, that is W2. And one more reading is there, weight of sand and cylinder, after pouring cone only. If you want to only pour the cone only, that means how much weight it's left now? 9005 grams. And one more part is there given, that if you have the cylinder, it's having some volume of calibrating cylinder. Volume of calibrating cylinder is actually given to you 1000 cc, 1000 centimeter cube, and the weight of sand in the calibrating cylinder, So there would be some calibrations. There would be some, let's say we know that there is some volume of, there is some particular volume of the calibrating cylinder. We will be knowing that there is some 1000 centimeter cube of the cylinder, and we know how much weight of that sand is inside the cylinder. We also know that also. So this part we also know. So from this one we can get what is the density of the sand. So let's go for the solution. Get the final problem is that get the unit weight of the soil. I would say from this statement, we can get the density of the sand. So your density of the sand would be actually equals to 1550 grams per 1000 centimeter cube. So that's actually 1.5 gram per cc. So this is your unit weight or density of the sand. So we got one of the part, and from these three statements, we can say what is the weight of the sand inside the hole. Let's try to get that solution. Can you tell me what is the weight lost from the calibrating cylinder when we filled the cone and the what you call as cone and the hole. So what is the weight lost? If I write what is the weight lost from this one, from this cylinder, that is actually initially it was 10500 grams. Now we have removed how much? Yeah, we have not written that. So your W2 was actually how much? 9450 grams. W2 was 9450 grams. It is talking about the left part. It's talking about that we have this one as W2 now. W2. That means some lost weight is there, and you subtract that lost weight. Now your left part of the weight is only 9450. So I would say the lost weight is actually difference of the two. Difference of the two. Can we say that? Initially it was this one, that is W1 entire thing. Now we have lost some value, such that it is the difference of the two. So that weight lost is actually how much? That's 1050 grams. 1050 grams. So this part is actually, this is, we can conclude that this part is actually, this is actually weight of soil in the hole, and sorry, weight of sand in the hole, and this is weight of sand in the cone. This is the sum of weight of sand in the hole, and this is the weight of sand in the cone. So this is the sum of the two. And one more data is given to you. One more data we can see. One more data is given to you. One more data is given to you. Weight of sand plus cylinder after pouring cone only. So if we say there was only cone, there was only cone, how much weight was, how much weight we had? So we had 9005 grams. But if you talk about both, we have 9450 grams. If we say the difference of the two would be because of the weight of the sand in the hole. Because here we have cone, here we have cone, and here we have some extra part of hole. And because of that, there is some extra reading. So I would say weight of the sand in the hole is actually how much? Yeah. Yeah, let's analyze this data. Let's try to understand what is this, what this means. Or let's try to understand what this means. Okay. So this is actually that. Firstly, let's say that this was your cylinder. You are filling that cone, and after that you are filling that hole. So initially when you fill only the cone, when you fill only the cone, let's say that I got stuck here. Let's say that I got stuck here. Okay. Okay. Let's finalize it that I got stuck here. The solution is that the solution is in this way, that that we say that the weight of soil, weight of the sand for the cone only, is that the difference of 9450 grams minus 9005 grams, and that's some value of 445 grams. 445 grams. It's that weight of the sand in the cone is only 445 grams, and there is one more part, that weight of the sand in the hole is actually that total was 1050 grams. It was because of sand, and it was because of cone and what you call as hole. Now we have to subtract that WSC. So this is that, what is the weight of the sand in the hole? That's coming to be 600 some value, 605 grams. 605 grams. So this is the weight of the sand in the hole. Weight of the sand in the hole, that is 605 grams. From this data, once we got that the weight of the sand in the hole, that weight of the sand in the hole is 605 grams. Now I want to say what is the volume of the what is the volume of the hole? What is the volume of hole? If you are pouring that weight of the sand in the hole equals to 605 grams, and it's having some unit weight of gamma sand equals to 1.5 grams per cc. Can you tell me what is the volume of the hole? So volume of the hole can be solved in this way, that we have this 605 grams divided by, we have this density of 1.5 grams per cc. So your volume of the hole is actually some cubic centimeter of 390.32. So this is the volume of the hole. Once we got the volume of the hole, we can say what is the density of the what is the density of the sand? What is the density of the soil? So your density of the soil is actually weight of the soil we have already calculated. That was 761, that was given to you as 761.25 grams divided by total volume of soil. Total volume of that hole, that's 390.32. So that's your what you call as solution for the problem. 1.95 grams per cc. So let's go for the fourth method. That's we say that's water balloon method. Water balloon method. Water balloon method is there. So name suggests that once you try to excavate that area, once you excavate the particular area, small area, then we want to say what is the volume of that particular, what is the volume because of that area. Okay, let's say this part we have excavated. Now we want to say what is the volume excavated. What is the volume excavated? That is actually volume of soil. So for the calculation of that volume of soil, we would say let's place a plastic sheet. We place some plastic sheet here. That's some sort of plastic sheet, or we can say there is some balloon also, or a balloon. Now we fill that sheet or a balloon. Now fill that sheet or balloon, with water, up to the top level, Then we would say how much volume of water has been filled in that sheet. What is the volume of water filled in that sheet? So that volume would be actually that volume of soil. That would indicate what is the volume of soil. So we can easily say we have excavated that, weight of soil equals to WS. This is the weight of soil we have excavated. Then we would say what is the density? That I would say weight of the soil divided by what was the volume of water you filled in the sheet, in the balloon. Okay. And one more method is their final method, that is radiation method. So this is your modern kind of thing, radiation method, that it's very quick. This is on-site, but this is very new method and it is gaining popularity. So let's forget that. And that's all from your gamma unit weight calculations. Thank you for watching that. Thank you.